Thanks a lot for the very kind introduction and for the invitation to present some research in this seminar. So today I decided to talk about some line of work that has been going on for some time. So you see the first paper is already 5 years old. So this is most of this has been work in collaboration with Sadvik Singh. So we started when he was an intern in my group, and now he'll graduate soon from Cambridge. There are two more recent additions to this line of work. One regarding random states. So as the host kindly introduced me, I'm also interested a lot in random matrix theory and intersections of random matrix theory and quantum information theory. So if you're interested in random quantum states having these particular types of symmetry, then check out this recent paper with Sang-Jun Park. He's a postdoc in Toulouse now. And there is also even more recent work with Sadvik and Abbas Gulati, who's a PhD student now, about some extra symmetry added on top of this diagonal unitary. I will mention this briefly during my talk. And now Abbas is working on the multipartite version of these things. But again, these are things that I will briefly mention during the talk. But basically, if you were to open just one paper from this list, it's this second one here, which I will mostly talk about. Good. So I plan to give a rather pedagogical talk. So I will. I don't know how much time it will take, but please stop me if there are any questions. I have an iPad, so I can write on the slides. Please don't hesitate to stop me. I hope that that this talk will be clear for everyone. But so here's a short plan. So this talk is about symmetric states in quantum information theory, and today I will be mostly talking about bipartite states, mixed states, bipartite density matrices, and I will be focusing on such bipartite states which have symmetry. I will tell you in a moment what type of symmetry we consider. But I will start simply by some very famous families of symmetric states in quantum information theory. That's point one. Then in point two, I will introduce the main topic of this talk, which is this new type of symmetry. Well, new. I mean, it has been studied for quite some long time, but without not in this unified framework that I will present today. But many examples of states having this diagonal unitary symmetry appeared in the literature all over the place. So we kind of gathered all these examples in this work and put a general framework around them. And maybe points 3 and 4 are about applications of these ideas. The first one is about separability and entanglement of these states. And the final one is about this PPT squared conjecture, still an open problem in quantum information theory. So I will, these are like more technical issues. If time allows, we will also go into this. But let me maybe start with telling you what is the motivation for this talk. So my goal today is to try to convince you that the states that I'm going to talk about, these diagonal unitary symmetric states, are a very nice family, a very useful family of states in quantum information theory. One that you should have always in mind when checking your conjectures or trying to find examples or of states or quantum channels or quantum states. So whenever you have some problem in quantum information theory and you want to test it or you want to have examples, the set of quantum states is too big. So then you look at very specific examples, and like Werner states, isotropic states, these are very well-known type of states. But it turns out that these very symmetric states are sometimes too simple. So what I want to argue today is that this family that I will introduce in part 2 of the talk, these diagonal unitary symmetric states, they're kind of intermediate between the set of very symmetric states and the set of all states, in the sense that the family is quite big. It's indexed by many parameters. So it's a big family. And also that it contains many interesting type of states. For instance, it contains PPT entangled states. which is not the case for much more symmetric families. So it contains many interesting quantum states which have interesting quantum properties for us on the one hand, and on the other hand, it's kind of simpler. It's kind of simple to analyze, both numerically and analytically. So in my opinion, it's kind of at the sweet spot between complexity and simplicity, in the sense that we can prove and derive results analytically about this family of states. So my plan is basically to give you this tool of these states, and to show you how to manipulate them and why I think they're kind of they're interesting. Okay. So let's start. Let's start with unitary symmetry. Okay. So just to fix some notation, I think everyone is familiar with these things, but if not, please again raise your hand or just interrupt me. It's easier. So this is the notation I'll be using. So density matrices or mixed quantum states. These are complex matrices, positive semi-definite. So I will use this larger or equal notation to denote positive semi-definiteness, and trace one. And we have the time evolution in quantum theory is encoded by unitary matrices. And for mixed states, this amounts to conjugating the density matrix by a unitary operator. Okay. And these unitaries a priori can be anything, any unitary operator. I will denote unitary operators by UD. Okay. And the idea of symmetry in quantum information theory is to look at states which are invariant by some kind of family of unitary operator, be it all unitary operators or some particular subclass of unitary operators. And here is the most basic example. So if you have a matrix X in MD, which is invariant by all unitary operators, meaning that UXU star. So another important thing is that for me, the star is the mathematician star. So this is actually the diagonal. Okay. I will be using the star, but think star is dagger. So it's the adjoint, it's the Hermitian adjoint. So if UXU star is equal to X for all U, then this means this can be equivalently stated that X commutes with all unitary operators, hence with the span of all unitary operators, and the only matrices which commutes with this whole span, which is a set of matrices, are the scalar matrices, so multiples of the identity. So in this case, the only solutions to this equation is X, a multiple of the identity, and asking that my state is a density matrix fixes this constant to be 1 over D in order to have the trace condition, trace equals 1. Okay. So this is an example. If you add the symmetry, I mean, UXU star equals X for all U, then we get just basically one density matrix which satisfies this, which is the maximally mixed state. Okay. So not very interesting. Things get interesting in this story, as in quantum information theory, when we talk about two Hilbert spaces. So bipartite states, bipartite matrices.
Ian, sorry, I have a very dumb question already in the first slide.
Oh,
so
sure. That's great.
If instead of the set of all unitary matrices, what is the smallest subset of unitary matrices that you would need so that you have essentially the same result, that X is identity? Is it just going to be something that spans them, like some basis sort of thing? Yes, exactly. Is it immediate?
So
like
we need that the span. I mean, we need. If you only get scalar matrices, then the commutator of scalar matrices is all matrices. So we need a subgroup which spans everything. And the unitary group does this, but also several subgroups of the unitary. For instance, the orthogonal groups also does this.
Okay.
So there are many groups.
You don't need them to be complex.
Exactly. I can only look at orthogonal matrices, for instance. This is also true that orthogonal matrices span, but and this is precisely the game we will play today. We will consider subgroups such that the span of the commutator is not everything. So we'll get more invariant states. That's precisely the game that the game will play. So the more symmetry you have, the less matrices having the symmetry you will get. So of course, if you ask no symmetry, you get everything. If you ask this full U symmetry, you get just the identity is not interesting. So we have to place this cursor on the size of the symmetry group in order to get interesting examples. And moreover, if the examples are physically motivated, as a mathematician, I'm a mathematician, you're even happier if you have some physical motivation. Okay? But kind of the idea is precisely this: to find a nice symmetry group, which is not too small, not too big, so that we get interesting examples. Okay? Good. Thanks for the question. So bipartite operators now. So we have Alice and Bob now. We have density matrices on a tensor product of two Hilbert spaces. We can do more actually. So in the papers with Sadvik, we developed the theory for more than two, but somehow it becomes a bit complicated for three or more. So today I decided just to stick to bipartite operators, and you'll see that we get enough meat on the plate to be happy with bipartite operators. But the same ideas can be generalized to the multipartite setting. Good. So that's one of the motivations is that entanglement appears when you have a tensor product of Hilbert spaces. You will have two. So now I will look at Alice and Bob. So, and bipartite density matrices, rho AB, which live on MD tensor MD. So both Alice and Bob have a Hilbert space of dimension D. And the conditions are the same, positive and trace one. Okay. And throughout the talk, since we'll be using tensor products, and you will see we'll play a lot with these with this tensor perspective on density matrices. I will use this graphical notation, this Penrose graphical notation for density matrices and for tensors. So you see, I will denote matrices by these boxes, rho AB. And such a box has four legs. It has two inputs, one for Alice, one for Bob, and two outputs, one for Alice, one for Bob. Okay. And the way to think about this is that these operators, these pictures, come with indices. So the whole point is to avoid writing indices and sums over indices and all the stuff. That's the whole point of this Penrose graphical calculus. So if I put some indices on this wire, you can think that the corresponding picture corresponds to the element rho ij kl. Right? So rho is a bipartite matrix. It has one input index which is parameterized by two indices from 1 to d because it's a two tensor. It's a tensor in Alice tensor Bob, and two input and two output indices. Okay. The idea, the main point is that a bipartite mixed quantum state is a four tensor. It has one input for Alice, one output for Alice, one input for Bob, one output. So we'll use a lot this graphical notation. If you're not familiar with it, I hope that during this talk you will get some familiarity. But I will explain things as we go. But please stop me if the pictures are not clear, or if you want more details about the pictures. We can also write equations with indices. But the point is not to do this, because at some point there are too many indices and it gets curious.
Can I ask a question?
Please.
So let's say on the previous slide, you had identity by D, and you had this discussion with Atul, and based on that, I'm trying to think. So let's say you had this should while duality, right? Using that, we know that if you are, looking at the kth order commutant of the unitary group, it's spanned by, basically the operators, the permutation operators, which are associated with the SK, basically.
Yes.
So
yes.
I mean, is that the game?
Oh, yes, sorry. Exactly. I will use for duality in a couple of slides.
I see.
Precisely.
Okay. No, I was trying to think, is that where we want to go?
This is where we want to go. Exactly.
Okay.
That's precisely. We want to find commutators. We will compute commutators, and indeed, sure-while duality is the main tool we will use in this full unitary group. And also in the second part of the talk, we'll have introduced this smaller symmetry group. But indeed, this is the mathematics. This is the essential.
So something related to that, I have this question then. So if we go to the previous slide, if we think of this u dagger equal to x, it's like basically you are trying to look for the fixed point of the unitary channel, right? I mean, I can think like
we want that.
So
everything is a fixed point.
Yeah. So let's say instead of just unitary channel, if I think of let's say more general channel, I mean, we don't have, I mean, or maybe we have, something like sure while duality. I mean, have people thought of that? Like, I mean, that's where I wanted to get to. Like, because let's say
Yeah,
if I'm interested in, like, I mean, more general CPTP map, and I want E of a row equal to rho, and for that, like, let's say I want 2 copies or k copies, and in that case, I'm interested in, like symmetries.
very good. So definitely, since we're going to talk about bipartite operators in this talk, this is the same as looking at Choi matrices of channels. So of course, bipartite operators having some symmetry is equivalent, if you look in the channel picture, to the channel commuting with some symmetry. So I decided in these slides not to talk about channels because I didn't want to introduce channels, and because everything is equivalent, everything will be equivalent via the Choi isomorphism. So one thing, so in any case, you can interpret many of the things I will say today in terms of channels and their symmetries. So that's one point. The second point is that I'm not going to talk about more than 2 parties. So my sure while duality will be related to just 2 copies of the unitary group. The same thing works for more, but again, I don't want to go there. And the final point that you asked was about if I look at more general channels than just unitary conjugation. And the answer is not. Actually, this thing only works if you have these rank 1 channels, so just unitary conjugations. But maybe you can please ask me. Feel free to ask me again later in the talk. Maybe things will be clear later, and some of the questions, the doubts will be dissipated. Okay, so just a brief slide on quantum entanglement. We defined quantum entanglement by the classical notion, which is separability. So such a bipartite state rho AB is separable if you can write it as a convex mixture of tensor product states. So this one of the nice features of the Stinespring graphical notation is that the tensor product of operator is just represented by if I write the picture for alpha I tensor beta I, then this picture is just the picture for alpha I and the picture for beta I superimposed, one next to the other. So this is one of these nice features of the Stinespring graphical calculus. So that's how we write separable states in this graphical notation. And entangled states are states which are not separable, with this famous maximal entangled state, omega, denoted by omega. So this is 1 over d, the projection on the sum of II. And graphically, this omega. So here's an example of how this graphical calculus works. Right? So omega is a bipartite density matrix, so it has 4 indices as before, I, j, k, l, and the picture for omega is just 1 over d, so I have to write this normalization by hand. And then you see I have these 2 symbols which corresponds to delta function, right? So this symbol here tells me that the index I needs to be equal to the index j, and this wire here tells me that the index k has to be equal to the index l. And I'm summing over these common indices I equals j and respectively k equals. Okay. So here's the picture. So forget about the indices I, j, k, l. Here's the picture for the maximal entangled state, and you see it's something which cannot be split in the middle like this, because these wires go from Alice to Bob, and this is what they mean morally, that Alice is perfectly correlated to Bob via this entanglement. Okay. So yes, so this is how you go from these type of pictures to formulas. And the idea, you should be able to do it the other way around. So if you have this formula to come up with this picture here, but you see it's not difficult. It requires some getting used to, but it's not difficult. Okay, so we have separability versus entanglement.
Sorry,
now let's look at.
Sorry, just a quick question, because I was wondering what the connection would be between. Okay, so yeah, maybe the best way to phrase it is, what would be the diagram, or in the diagrammatic notation, how would we represent classical correlations as opposed to entanglement?
so the classical correlations here in the top picture for separable states is via this P. Right. So if I were if I were to draw the full picture here, I could draw it something like this. Right? So the sum over I of Pi is now represented by this middle wire here, P. But the whole point is that this middle wire, what's the difference now between this picture here and this picture here? Fundamentally, the difference is that here I have only one wire which crosses from Alice to Bob, which is this classical correlation via the probability measure, P. And here I have two wires which cross from Alice to Bob. So think about this is like probability vectors, and think about this is like two wires in this matrix correlation, so like quantum correlation, quote unquote. But this is a bit metaphysical, so. But in any case, this is what a classical correlation would be. This summing over P. So you see, you have this wire which is fully connected, so I have to sum over it, and this corresponds to the sum on top here.
Okay.
But then in this picture also, I have to tell you, because here what's important is that these matrices alpha I and beta I are positive semi-definite, are quantum states. And here, this alpha object now has three legs, meaning that it's just, I'm stacking my alpha i's one on top of the other. So, it becomes a bit cumbersome. This is why I decided not to write it like this.
So what's the characterization of alpha then? Like is it a matrix? No, it has three indices now, right?
Yes. So this alpha object has now three indices. And what I would say this for all I. This is positive semi-definite.
I see. Yeah, it makes sense, but yeah, thank you.
And if I can go further with the pictures, but I don't know if this will help. Let me write it differently. I can put the I here since I put it there. So this means that for all I can write alpha I as xi times xi dagger, which is equivalent to alpha being positive semi-definite. Now since I have for all I can erase this. This is this condition that for all I the alpha is. So you can go quite far with these pictures, but at some point, yeah, there's no point for what we've been doing.
Okay, thank you.
Good. So as before, we will ask that these these matrices, these bipartite matrices X, are symmetric with respect to the full unitary group. But now, of course, I will not take the full unitary group because there's no point. I'm trying to talk about separability and entanglement. So what's important here is this tensor product of unitaries, so local unitaries. So this is what I'm asking here. I'm asking that my matrix X is invariant by conjugation by U tensor U. Okay. For all U in the individual spaces of Alice and Bob, I require that Alice and Bob have the same Hilbert space, CD. And I'm asking this condition here. So with pictures, I'm asking this condition. That if I have X and if I multiply it from the left by U tensor U and from the right by U star tensor U star, I get back X. So this is what we call UU symmetry. And the theorem, which is a simple application of Schur-Weil duality. I didn't want to say these words, but since they have been mentioned, I can say them. So it says that the commutant of this U tensor U is actually the symmetric group on two elements. And this is what we're doing here. This is what this graphical inequality says, that if X commutes with U tensor U for all unitaries U, then X lives in the span of two operators, this one, this one. The first one is the identity. It means that Alice's indices have to be the same, Bob indices have to be the same. And the second one is the flip, the flip operator, which permutes tensors, permutes Alice's tensor with Alice's input with Bob's input. Here. So this is the statement of the thing, and it's sure-while duality in a very simple case. And you see, one of the advantages.
Sorry,
Yes,
one next question maybe. So when you are talking about this set X of this bipartite operator, can we think this class of state as in free states in context of resource theory, that those set of states X which is maintaining this symmetry?
I'm not at all familiar with resource theory. I've heard talks about it, but I'm not yet in this mindset. So I think you can. I don't know if it makes sense more than this. I really cannot answer. I don't know what is important in resource theory, what is not. It's hard for me to.
Okay.
Sorry. But what I was saying is that so there is this implication here. This is very easy to show that if you have an X which is of this form, then X automatically has the symmetry. And why is this? Because you see, if I were to put my unitaries U star, U star, they will cancel. You see, I will move U to the wire and it will cancel the U adjoint C's. And the same on the bottom wire on Alice. So I can just move this U here, this U star, I can move it and it will cancel. And it's the same story with the other matrix. Now the U's will cancel, but they will cancel diagonally. Canceling on Alice's size and modes. So you see, what I want to say is that this class of the identity and the flip are the operators which I can represent with wires, which make this cancellation, which make this equality here trivial on the left-hand side. Of course, the hard implication is this one, to show that there are no more than the vector space spanned by these two. Okay. So this is why, for instance, it's a nice application of this graphical calculus. You can see that the identity and the flip have trivially this symmetry because the U's cancel basically.
If I can use the, like the regular, again, sure-while duality language, sorry about that.
Yes, sure.
Like we know that, like, I mean, we are talking about the second moment, the commutant is generated by identity and flip.
Yes.
Where this alpha and beta like should depend on X, right? I mean, like, do you have some characterization of alpha and beta? I mean,
we can get them, of course, but this is not the point. I mean, sure, you're perfectly right. I can find alpha and beta in terms of X, like in terms of trace of X and trace of X times flip. That's we can do this. But here I just wanted to say that X lives in the span of these two operators. I don't care too much about the coefficients.
Okay. And basically for the hard direction, do you use sure-while duality, or is like some other argument to get the hard direction, like here to prove the hard direction?
This is like a 4-pro result. I mean, I don't know how people did it the first time. I don't even know how to. Probably Reinhard Werner is responsible for this, but probably yes, he used sure-while duality. I don't recall historically how this has been shown, but indeed, sure-while duality is the correct way to think about this.
Okay.
And you see, if you have more than two legs, that's precisely you get all the permutation operators between the k inputs and k outputs. So
yeah, because I mean, you will remain inside the commutant, right? And if the commutant is generated by, like all of these elements of SK, then that X will always has to be represented as, like linear combination of, like those element, like symmetric unitary matrix, like this elements IF and higher order terms. And the other directions you have, like using graphical calculus, you have shown that holds. So you're saying that the hard direction follows from the sure-while duality, and the other direction follows from the
it's just obvious.
from this mat, like
Precisely.
diagrammatic calculus. Okay, I see.
Precisely, this is correct. Okay, so the conclusion of this slide is that if you ask for this bipartite operator X to commute with this UU, then you get a vector space of dimension 2. So there are matrices spanned by the identity and the flip. And if you want quantum states, these are called the Werner states. Right? The Werner states are the because here I didn't say anything about positivity or about normalization, but if you want positive semi-definite matrices with trace 1, then what you get is the famous Werner states, which you can also write because the flip you can also write it like projection on the symmetric. So if you are familiar with this, so this flip is also the projection on the symmetric subspace minus the projection on the anti-symmetric subspace, and then X you can also write it like A PS plus. So let's see, alpha prime PS plus beta prime P anti-symmetric. So it's the same as the span of the symmetric and anti-symmetric projection. But if you are not familiar with this, it's just Werner state. It's a well-known family and well-studied family of bipartite states. Okay. So here is a twist to the previous slide. Instead of looking at U tensor U, let's look at U tensor U bar, because quantum theory is a complex theory, so I can put this bar. This changes a bit things. And again, with pictures, this is the picture I want. You see that the only difference is that, let me zoom in here, if I can manage. The only difference that here I have a conjugate, a complex conjugate entry-wise of my unitary matrix, and here I have the transpose. Right? The adjoint of the conjugate is the transpose. So if you ask for this equality to hold for all unitaries, then it's the same story. You see, morally, I have to cancel the U's. I need to get rid of my U's for this to hold. So it should be possible inside. If I look inside rho, I should find some wires which allow me to cancel these U's morally. So there are two ways to cancel the U's: horizontally, like this. This corresponds to this identity operator here. And I can cancel them like this.
I think there's a question in the chat. Also, please interrupt and ask directly. I mean, there's no need to raise hands.
Thanks, because I'm not, I cannot follow well the chat. Now I see the raised hand. Please ask the question. It was written, sorry. Let's see. It was not written.
Okay, I think maybe it's an error. Sorry, continue. I think they may have accidentally raised their hands.
I'm
sorry for the interruption.
No worries. Please stop me later if needed.
I think you have to unmute yourself. Hello?
Yeah, the person is muted, yes.
We cannot unmute you. You have to unmute yourself.
Good. So now
I'm sorry. I think there's a bit of a technical issue because I muted him in the beginning when we started the talk because his microphone was on and I don't know how to unmute him now. So that's very unfortunate. I'm very sorry for this. Maybe you can type your answer while we continue the presentation. Yeah, and we'll get back to your question. I'll read it out.
Okay, good. So I will continue and then
please continue. I'll read out the question. Yeah, I'm so sorry for this.
No worries. So I was telling that one way to cancel the unitaries was to cancel them horizontally, but there is also this other way to cancel them. So before we had the flip, now we can cancel them like that. And you see so this is something which appears in quantum information theory all over the place, and this is why we use maximal entangled state a lot. It's because of this property that if you have a unitary operator and this maximal entangled state, and here I put the conjugate of U, then you see this picture here, it's the same as I will take this box here and I will drag it on top. But you see, when you drag it, something strange happens. It's that it gets transposed. Its input will become output and vice versa. So this is the same as U. And this will be U bar transpose. Okay. And then this is the same as just the identity, because U bar transpose is the adjoint, and it cancels with you. So this is how we cancel the unitaries in this way. Okay. So it's the same story as before. It's only that we change directions in the way we cancel them. Seems to. And the conclusion is that now, yes.
But that's only one direction, right? The other direction still follows, but that shouldn't follow from Schur-Weil, right? No, because that is only Schur-Weil is only for
This is correct, but to do it via sure-value duality, what you would have to do, you will have to put UU on the left-hand side and U adjoint on the right-hand side. And to do this, what you will need to do, a partial transposition. You need to do this. And then the U will become back to flip. And you see, if I partial transpose this operator here, basically I'm swapping input and output downstairs. I'm not doing anything because it's the identity.
Right.
And if I'm partial transposing this guy, I will get the flip.
Becomes the flip. Yeah, exactly.
So this has also been studied a lot recently, especially by Studinsky and Polish collaborators. This is called the Wald-Brouwer algebra. So there is kind of also a sure-value duality. It's a bit more technical, but it's the same ideas basically. When you have this partial transpose, basically, if I were to say it one sentence, it will be partially transposed sure-value duality. So there is a lot of work. It's a bit more technical, but it has been done. We have the same technical tools to deal with this type of situations. Here it's very easy, but in general it's much more complicated if you have more parties.
And this doesn't arise for real matrices, right? Like if for orthogonal matrices, this would not be.
Yeah, exactly. Because here. I mean, so what it will be a difference. So for orthogonal matrices, because for orthogonal matrices, I can cancel them in both ways, right? There is no difference between O and O conjugate. So this is called the Brouwer algebra. So you will get the three things in the orthogonal case. You will get identity, flip, and the maximum.
Yeah, right. Hello.
Exactly.
Can you hear me?
Yes, I can.
Yeah.
Yes.
Sorry,
yes,
I can now unmute myself. So
yes.
Thank you. So I have a question that if you could go to the previous slide. I think that if you take a tensor product of two unitaries, then it would also be again a unitary on the tensor product space, right?
This is correct.
Then,
yes.
Then by the Schur's lemma, right? I believe you have been using Schur's lemma, right?
Not exactly. I mean, we have been using sure-value duality, but in that there is a use of Schur's lemma. Yes.
Yeah. So I'm just wondering mathematically, where is the room to get this term, which is the flip operator? Because if yeah, mathematically, diagrammatically, I can understand.
Like, because the representation. So because the representation U gives U tensor U, it's not irreducible.
It's not unitary.
It's not irreducible.
Okay, it is reducible, so you can write it as a sum of two.
And exactly,
blocks.
exactly. Before, if I have one copy of U, it is irreducible. So this is why I only get this identity. But if I have two copies, and that's the whole point of sure-value duality, it tells you what's the commutant.
I see.
When I have two, and exactly so, and if I have this, I can put even more. This is the sure-value duality, and this Brouwer algebra is I have orthogonal matrix instead of U. This also has been studied, and now I can also put some conjugates on some of the U's. And this is this Wald-Brouwer algebra, which has been studied a lot by this group of mathematicians from Poland. Studinsky, Osmaniek, and all these people have a couple of papers in which they develop this theory in great detail. Very, very nice papers. With applications in many topics like cloning, so it's really a very nice work, a very nice body of work.
Thank you.
Thanks for the question. Okay, good. So so here we were discussing this. We have this extra conjugate on the U, and instead of identity and flip, we get the identity and the maximally entangled state. And these are these isotropic states. These are called the isotropic states. And so basically, it's if you look at quantum states, imagine that this rounded triangle is the set of quantum states. The maximally entangled state is a pure state, so it's an extremal point. The identity is somewhere inside. This maximally mixed states on two qubits is somewhere inside. And these isotropic states are just a one parameter family of quantum states. Okay, so with this picture, what I want to say is that these isotropic states are a one parameter family, right? So I just have this parameter P. which is from a little bit less than 0, this portion here. But yeah, think about from 0 to 1, whatever. One parameter friend. Okay. Good. Now, I already discussed a bit partial transposition because there was this question. So, for deciding whether a state is separable is an NP-hard problem. So, in general, we don't have efficient tools to answer the question whether a given state is separable or not.
So yes. Before you start with the next thing, I had a very small, quick question. So this was for bipartite, right?
Yes.
So the number of parameters, do you know how they scale as you increase the number of systems?
So it will scale like a k factorial because of pure value duality.
The permutation thing. Okay, right.
Exactly.
Okay.
So
the space does increase quite rapidly as you increase the system size. Okay. Like the space of states increases quite quickly. Okay.
This is correct, but notice that it doesn't depend on D.
The dimension of the system, I see. Okay. Right.
That's one of the nice features of these pictures is that when I draw a wire, this corresponds to the Hilbert space CD, but I don't see the dimension. I mean, right. So I will have k factorial diagrams, my k factorial permutations, but it doesn't depend on D.
I see. Another very quick question, because I was looking at some infinite dimensional stuff for some other project, and I wonder, do all of these things also go through for infinite dimensions, or do we assume that D has to be finite?
I prefer, I don't know. I prefer to answer I don't know because I'm really not familiar with the subtleties of infinite dimensions in this case. I don't know.
Okay. Thank you.
Good. So yes, this partial transposition criterion is a very famous, result. The idea is that if you have a separable state, and if you transpose just one of the factors, let's say the second one, and act with the identity on the first, on Alice, and if Alice does nothing and Bob does a transpose, then the end result will still be a positive semi-definite matrix. So this is graphically how we represent this partial transpose. We just permute input and output for Bob. Alice, we don't do it. And so any separable state satisfy this positive partial transpose criterion. And if a density matrix doesn't satisfy it, then it's necessarily entangled. And we know that the converse is true only for small dimensions. So only 2 tensor 2 and 2 tensor 3. Now, let's go back to our Werner and isotropic states. So these were states which had this UU symmetry or UU bar symmetry. It turns out that for these families of symmetric states, the PPT criterion is necessary and sufficient. So if you have such a symmetric state, to decide whether it's separable or entanglement, you just have to compute its partial transposition. And as I mentioned it, but I didn't write it, if you take the maximal entangled state, remember this was the picture for the maximal entangled state, and you do the partial transposition, this was flipping input and output, then what you get is precisely the flip operator. Okay. So this partial transposition changes between isotropic and Werner states. Is this it's this involution which maps isotropic to Werner states and vice versa. Okay. So basically, we're in this partial transposition plays nice with this unitary symmetry. I think I mentioned this quickly with respect to one question. So in this respect, we don't have, so as I said, the PPT criterion is not always equivalent to separability. So people are interested in studying states which are PPT and entangled. They also have some applications to many areas in quantum information theory. For instance, you cannot distill maximal entanglement from them. So many interesting questions and conjectures related to this PPT entangled states. And the conclusion is that these states of that the symmetric states with UU symmetry or UU bar symmetry, the isotropic of Werner states, they don't contain PPT entangled states. So it's kind of they're not so rich because it's only one parameter family, so they don't contain this interesting phenomenon, this PPT entanglement. And actually, the same holds true if for these orthogonal tensor orthogonal symmetric states. This is called the Brouwer states. And even for a more, even if you further decrease, if you take something in between these hyperoctahedral states, which are, you add some extra symmetry on the levels of the CD space, but let me not get into this. Okay, so the main point is that in this family of full unitary symmetry, we don't have PPT entanglement. And as you guessed,
I'm sorry.
Yes.
So we're trying to weaken the symmetry group, right? So is maybe I misunderstood, but the hyperoctahedral,
Yes.
hyperoctahedral states. So these are a bigger set than Brouwer states. Is that what you're saying?
No, that's smaller sets.
Because you're increasing the
group,
amount of symmetry. You're increasing the size of the group.
I will tell you precisely in 3 slides what are the hyperoctahedral states. I just mentioned it here to say that these families don't contain anything because the symmetry group is too big, so my family is too small. My family of states is too small. So now the idea is to make the symmetry group smaller and smaller until I get enough states that contain quote unquote interesting quantum states with interesting properties for us.
Right.
And that's the point.
Can I quickly ask for the motivation for why we are trying to classify things this way? It looks very difficult to do it, but I guess you said something about proofs being easy, or it's easier to analyze.
Exactly.
Maybe it'll become clear. Maybe, yeah. Feel free to ignore the question now and answer it later if it's better.
The question is very good. So let me tell you. So there is the mathematician's answer, which says that this is a family of states which has symmetry, so it has less parameters, so it's easier to analyze. I mean, it contains tractable examples. But then there are also the quantum information theory's answer, which, for instance, if you look at the problem of cloning or of these, you cannot, in quantum information theory, you cannot clone quantum states perfectly, but you might ask what's the best cloning machine which takes qubits and gives you 2 qubits, but of course you cannot expect them to be perfect copies, but you have some fidelity. So this is a question about this quantum cloning, which was answered by Reinhard Werder also answered this question. And actually, if you think about it, if you think about these very general cloning machines, you can assume without loss of generality that they have this U tensor U bar symmetry. These quantum channels, because fidelity is invariant. I mean, the fidelity is invariant by unitary conjugation. So you can just twirl. I don't know if you're familiar with this notion of twirling. So if you have a channel, you can symmetrize it via some symmetry group, and you can show that the best cloning machine, if you twirl it, you get a cloning machine which has the same quality but has the symmetry. So it's Choi matrix will have this symmetry properties. So then, instead of looking for these cloning machines, quantum channels, which are arbitrary, I can just focus on my symmetric cloners, which are much easier to analyze because I have much fewer parameters. That's kind of the idea, to use symmetry to simplify the problems, as we usually do in math, physics, and I think science more generally. So,
thank you.
Yeah. I see if there is a question if the other side is visible, but I think it's not for me. Good.
Yeah, that was very early on. We sorted it. So,
yeah. Okay, good. So good. So now that's the point. We're going to make the symmetry group smaller in order to increase the size of symmetric states. And we're going the idea is that instead of looking at all unitary matrices, I'm going to look at unitary matrices which are diagonal. Okay? So a unitary matrix which is diagonal, it means that on the diagonal, I need to have phases. So I need to have complex numbers of modulus 1. And if I'm in the orthogonal case, the diagonal orthogonal group is just plus minus ones on the diagonal, 0 on the off diagonal. Okay. So this is a nice point. How do I represent graphically these diagonal unitary matrices? So before, a unitary matrix was a matrix, so a box with input leg, one output leg. Now I have this extra constraint that the matrix is diagonal. So there is a delta ij. So this delta ij is symbolized by this wire. And the actual value, it's not 1, it's this phase ui. So here, these are this, I should have said that ui are This is E. Yeah, you know, square root of -1 theta I. Okay, so this is how we represent these diagonal unitary matrices. It's diagonal because the input and output are connected, and I get this color coming from this vector, depending on the actual coordinate. Okay. So I'm going to play the same game. First, let's forget about bipartite matrices. Let's go back to the one part, just Alice. Remember, before with the unitary case, we only got multiples of the identity. Okay. And the condition was this, that if I conjugate my matrix X by a U, I get back X. This is the condition. And you see, it's the same story. I mean, this is one of the points that I want you to take away from this talk, is that if this is to be true for all U, I need to have a feature of X which will allow me to cancel the U's. As before, we had wires, so I could cancel the U's. Now I have these things which move on these, you know, they are vectors and they move on these wires. So basically, the way to cancel them is that X actually has built in this. It's a diagonal matrix. So it has built in this thing which tells me that the input coordinate has to be equal to the output coordinate. And this blue wire here allows me to, if I have my U box here and the U bar here, then I can move my U here, and I will just U bar equals 1. So they will just cancel each other out. So this is just a technical detail, but the moral of the story is that even in the one-partite case, I have more matrices. Before I only had multiples of the identity. Now I have all diagonal matrices which have the symmetry.
Excuse me, I have a question.
Yes, please go ahead.
What should I do if I want to have block diagonal thing in the picture? So here it seems that the matrix X will be diagonal in some fixed basis.
Mm-hmm.
But if I want to have some coherences in some blocks, then what should be the symmetry? Like, what should it look like?
Very good question. So first, let me pinpoint something that you said, which I should have said. You said that the matrices should be diagonal in some basis, and this is true. So before, everything was basis independent. Everything was kind of canonical. Now this is not true anymore. We have fixed the basis simply because I'm looking at diagonal unitary matrices which are diagonal in some basis. So again, my matrix X should be diagonal in the same basis. So now we have fixed the basis. Before we did. Now we have fixed the basis. This is very important. So now you asked me, how should what kind of symmetry should I use to get block diagonal matrices? So let me give you a partial answer. One way to do this is to have an X which is bipartite and to ask symmetry just on one set of wires.
Okay, so what kind of like block diagonal structure will it give? Like, will it give you the most general block diagonal structures, or?
This will mean that, so if I denote this by so Xij now, so let's say this has dimension D here, and this has dimension N. Okay, so Xij was, if I just fix Ij, the top indices, what I get is not a number, I get a matrix in NN. And what this means, this diagonal unitary means that this Xij is just delta Ij Xi. So morally, this means that my matrix X will be block diagonal like this: X1, X2, up to XD.
Someone is disturbing. I don't know who is that.
Yeah, there is some. Good. Thanks.
Yeah, I muted someone. Sorry. Yeah.
So yeah, this is a partial answer.
Yeah, let me just understand. So if I want to generate different blocks, then I have the tuning for this I and J block, right?
So with this construction that I drew here in purple, you can only get block diagonal matrices where the blocks have the same size n. You have D blocks of size n. If you want different sizes, then I cannot really do it because it's not a tensor product kind of thing. So if you want different block, then I cannot use these pictures, but this is kind of the idea somehow. That you have this extra wire, and this diagonal unitary only acts on the wire which you want I equals j. You want to have diagonal.
Right. But it should be possible in some way, right? Because, for example, if I, instead of saying the symmetry in this way, I can generate U through some other symmetry. For example, U commutes with the Hamiltonian, and then I want symmetry with respect to that unitary, then I will get a block diagonal structure.
Definitely. I mean, this is the point of this is how one diagonalizes big Hamiltonians which have symmetry. That's precisely, it's exactly what you're saying.
I see. Let's go and let's see.
Good. Okay, let me.
And one small quick question before. So did we explain how you prove this? Because one direction I think you sort of hinted at that if it is diagonal, it would work. The other direction I wasn't sure. I feel.
It's in this case it's just a simple computation because so what happens, what happens if I look at the ij element here? What I'm saying is that the left hand side is ui xij uj bar. This has to be equal to xij for all I, j, and vector u. This is what this equality, this picture equality looks like in coordinates.
Okay.
And now you see that if I take I different than j,
have to be, yeah. Okay. Thank you.
One last point on the slide is that here the x, the dimension of, let me write it like this, the dimension of x symmetric space is D. Before I had vector space of dimension 1, it was just a vector space spanned by the identity. Now I have a vector space of dimension D, all diagonal matrices. I have, D parameters in X. So I have the set of my invariant matrices. The dimension of the vector space of invariant matrices scales with the dimension of the Hilbert space, which we didn't have before. That's already good. This is a good sign. It's a good sign. And these diagonal matrices are a good are something in between the identity, just the trivial matrix, and the full set of matrices. It's a good it's something in between. It's not too big, not too small. So we're happy with this. But now let's talk about bipartite case, okay? Which is the so this is the finish. This is the main definition of this talk. I see we're already closing 1 hour. But yeah, I mean, I think there are many questions, so I think this is very positive. So let's continue. Please tell me for how long should I talk? I mean, I would like to have maybe at least 10 more minutes. If this would be excellent.
This is an hour and a half normally, so you have about half an hour more. This is that I will personally have to leave, unfortunately, because I'm traveling, and but I'll watch on YouTube, so very much looking forward to it. So yeah, please continue. You have at least half an hour.
Yeah.
Good. Thanks a lot. It's very generous. We almost never have that much time to give talks. Good. So as before, we want to write the symmetry in the case of bipartite matrices. So now we have Alice on top, Bob on bottom. We have inputs here and outputs here, and we have all these possible choices. We can play with the bar as we did before. So this is the UU invariance. This is UU bar invariance. And this is the orthogonal case in the bottom. Okay, so it's as we had in the unitary case, but now we have this diagonal unitary. Sorry, we have diagonal unitary. So we have we don't have these boxes which act on the full wire. We just have diagonal boxes which come on top like this. But it's the same. Basically, it's the same idea as for Werner and isotropic states. So this is like the Werner states, but with diagonal unitary instead of full unitary. This is isotropic states with diagonal unitary instead of unitary, and this is the orthogonal version of. And we call this, there is some acronym. We call this LDUI, local diagonal unitary invariant, CLDUI, conjugate, because we have this conjugate here, and LDOI with orthogonal instead of unitary. So this definition just clearly adapted from what we learned from the fathers of the theory, from Reinhardt and company, about the symmetric states, adapted to this diagonal. We have the group smaller, we have just diagonal matrices. Okay. And this is the main theory. So this is the starting point of everything. Like before, remember, before for Venn states we said states which have so matrices which have this invariance lie in the span of identity and flip, and for isotropic we had identity and maximum entanglement. Now it turns out that we have a much richer class of states, and this is how we parameterize. So let's look at CLDUI. So CLDUI, remember CLDUI was the class where I had U bar, and U. And as always, if I want my state to be invariant, I need to be able to simplify the U's with the U bars. So I need them to be able to slide these boxes, to slide the boxes here, in order that they meet them. So one possibility is to cancel them in this way. And you see, if X is of this form, we will discuss later how this looks like, what this, but just look at the picture. It means that I can take this U here and slide it all the way to meet this U bar here, and they will cancel. And the same on the bottom. They will slide over this point. Now, same story with the B. I can slide the U here. So let me draw it, maybe it's easier to see. The U was here, the U bar was here. And you see, I can slide it like this, and they will cancel. Okay, so it's like for the maximal entanglement state, I could slide either horizontally or vertically. It's the same story, but now it's easier to slide because these are just diagonal matrices where I can move them along the wires. Right. So morally, this is what this theorem says. It's that the matrices X, which have this symmetry, lie in the span of matrices of this form and of matrices of this form. There is some technicality because I have to ask that they have the same diagonal to avoid counting things twice, because technical reason, forget about this delta. It's basically the matrices A and B need to have the same diagonal. So I'm counting the diagonal twice. So I'm taking value out here just to count it once. Technicality, don't worry about. Now, what are these beasts? What are these two matrices here? So here, the matrix, so A, you see A is an object, A is a box, which has two wires, right? One input, one output. So A is a matrix. And so what I have here, it's a bipartite matrix, which is built out of a single partite matrix, just by putting the values of my matrix Aij into some precise corners of the matrix Xijkl, right? So I need to have some indices to be equal, which correspond to these wires, and the same for B. And basically, I'm taking my matrix A, the element of the matrix A, and putting it into this big bipartite matrix at some specific basis. So this matrix X here, the matrix X here, you see, it has d to the power 4 coordinates. It has 4 indices. It's a bipartite matrix, so it has d to the power 4 coordinates. And actually, what we're seeing here is that this is a very sparse matrix. Among these d to the power 4 coordinates, I only have order of 2 times d squared coordinates, the things where A appear and the things where B appear. And even less, it's 2d squared minus d because they have the same diagonal somehow. Okay? So these CLDUI matrices are very sparse matrices, and they are parameterized by 2 single party matrices. Okay, this is a lot to take in. I realize that this is the slide. This is the most difficult slide. We'll see some examples on the next slide if there are no questions. Yeah, let me skip this. This is the same story for the other types of matrices. Let's skip it. So here are some examples that we have seen before. The identity matrix. The identity matrix is symmetric with respect to all the things we have seen before. These full unitary groups. So since the full unitary group is a bigger group, it also has the smaller symmetry, this diagonal unitary group. So it's of this form. Actually, it's of the form when the matrix A, this will be my matrix A, is this J matrix. This is the all one matrix. So all this, so remember the picture was something like this. So basically what I'm saying is that if A is the all one matrix, then it doesn't do anything. It doesn't affect my wires because it just gives a coefficient of 1 to the top wire, a coefficient of 1 to I just get the identity matrix. And the same story with this B matrix. If I take B to be J, this all one matrix, I get the maximal entangled state, right? Because this one vector here gives me a coefficient of 1 to this thing, and this is the maximal entangled state. And the flip is again part of this class, but with some different choice of how to put the wires. It's not very important. Okay. So this is, I'm just saying something simple, that the matrices which are full unitary invariant are also diagonal unitary invariant, and they correspond to this very simple choice of taking the all ones matrix for the matrices A and B. Okay. So our class contains, of course, the smallest class of Werner and isotropic states. But Werner and isotropic states are a one parameter family. Now we have something which has d squared, order of d squared parameters. So as d increases, Werner and isotropic states, the number of parameters doesn't increase. And for us, it increases with d squared, which is still much smaller than the total size of density matrices bipartite density matrices of size d4. So this is this idea that it's intermediate between the two. Okay, these were just two examples. Yes, this is what I was saying. Let me these Werner and isotropic states that they correspond to, even if you have, you know, like with these parameters A and B, right? If I have A times the identity matrix plus B times the flip, or in the isotropic case, A times the identity and B times the maximal entangled state, this corresponds to the states where the matrices A and B are mixtures between the identity and the all ones matrix. So these are the simplest possible cases. And there is also this mixture of Dickey states, which is some other family of states which has been studied a lot in the literature, and they correspond to A equal B in the picture, in this picture here. Pictures. But I'll get back to this in a moment. And actually, there are many examples of states that people have studied for their entanglement properties, for their partial transpose properties, even channels. You know, if you look at channels to their Choi matrix, this famous Choi, the famous map discovered by Choi, which is a positive indecomposable map, is also part of this family. So with Sadvik, we look at many papers in the literature where such symmetric states are discussed, and we can find many examples of states, families of states studied individually that fit this framework. So it's a quite general class. Okay, now I told you about what I've did up to this point is just linear algebra. Now I want to discuss some quantum information theory. So I want to discuss some positivity property, positive partial transpose, separability, and get into this more physical notion. Okay.
Before that, can I ask a question?
Please do.
So there was, like recently a paper from Jens Isart, Lorenzo Leone, and others, where they developed, like a theory for Clifford commutant.
Yes.
And yeah, like they had, like this similar kind of, they had also this graphical calculus,
Yes.
but they applied it mostly to magic, I believe, and I did not see anything
Correct.
like this what you're talking. So are you already working on that? If not, like, do you think that's a good that's exactly thing to try and see?
So so I think it's the same kind of idea of program to carry out, but it's completely different symmetry classes.
Okay.
it's the same. I mean, you have different groups. You have stabilizer groups, and here we have these diagonal unitary groups. I mean, they're a bit different, but the program is the same. I mean, basically, try to find the structure of the symmetric states using linear algebra, and then since you have these symmetric states, they have fewer parameters, and try to get information about your state from this simpler set of parameters. It's kind of the same idea, the same program, but it's different mathematics, I guess. Different groups, so different mathematics.
I see. Okay, thanks.
Yes. So here is one type of result that we can mention. So here I did it for this LDOI for the orthogonal case, but let me let's forget about the C part. Let's forget about the C part to have things simple. So you have this operator X. Remember, X was a bipartite operator, and you could write it in terms of this matrix A. And this matrix B. Let's not worry about this common diagonal and all this stuff. I mean, they're just technicalities. Okay. So to every pair of matrices A and B having the same diagonal, I can build this matrix X, which has the diagonal unitary symmetry, and vice versa. Okay. So symmetric matrices and pairs of matrices A and B are the same thing. And now it turns out that the condition for the matrix X, for the big matrix, to be positive semi-definite, it's actually very simple in terms of the matrices A and B, in terms of the parameters. Actually, for X to be positive semi-definite, A has to be entry-wise positive. So the entries, all the entries of A have to be non-negative, and B has to be positive semi-definite. And to see this, one way to see this is that if you write really this big matrix X, then actually on the diagonal of X, you will see the matrix A. Remember that X is bipartite, it's of size D squared. So it's a vector of size D squared. And actually, this diagonal is just the matrix A flattened. Just you take the D squared and you put it into a big vector, and you put the vector on the diagonal. So this is why A has to be entry-wise negative, because it's actually the diagonal of my positive semi-definite matrix. And the matrix B is actually a submatrix. It's a minor. Didn't want to do this. The matrix B is a. This is B. It's a submatrix of X, and you can see it even from this picture that basically what you're doing, you're embedding this matrix B inside X in this kind of symmetric, in this I equals I case, like the maximal entangles. So this is why, since B is a submatrix, is a minor of a positive semi-definite matrix, it has to be positive semi-definite, and it's an if and only if statement. So this hints to why this class is so nice, because you see I have this object X. It's a matrix of size D squared. It's a big bipartite matrix, and the property of X being positive semi-definite, I can express it in terms of much simpler objects. These objects A and B, which are just of size D. Okay. So I get a drop in complexity. I mean, for this. For the properties of X in terms of property of these two parameters A and B. Okay. If you think of A and B, are really the A and B play the same role as this parameter here, this parameter P in isotropic states. It's just a parameter of the family A and B. Instead of just being one scalar, there are two matrices, but they play the same role. Moreover, all the operations you can imagine doing on these matrices X, operations of the special for like transposes or flipping the indices or partial transposes, these correspond to very simple operations on these parameters ABC. For instance, if I flip Alice and Bob on the input and on the output, I'm just putting a transpose on A and a transpose on this third parameter C. If I'm taking the full transpose of the matrix, I'm just transposing B and C. And importantly for us, if I take the partial transpose of an X ABC matrix, I'm just swapping B and C. Just as I told you, partial transpose goes from the to isotropic. Partial transpose just swaps B and C. So this family of symmetric states is stable under these operations, and these operations are easily readable, implementable in terms of these parameters. And you see now, this will be important for us. If I have a matrix X which has, forget about the C, which has A equals B, then for it to be PPT, well, we need that A has to be, this matrix A has to be at the same time non-negative. This was the first condition before, and positive semi-definite. This was the second condition before. Okay. So these matrices which are at the same time positive semi-definite and have non-negative entries, these are called doubly non-negative matrices. Okay. So it's and one final thing is that the trace of the full matrix X is given by the sum of the entries of A, and the partial traces of X, something which also appears if you think about Choi matrices. The partial traces are this normalization condition, so these are important objects that we need to consider. They can be easily expressed. For instance, this partial trace over the second leg of A are just, so let me write here. So this is trace 2 of X. The picture for this is X, and I'm tracing here. So this matrix here is just the partial trace of X is just take your matrix A, multiply it with the all one vector, you get a vector. These are the row sums of A, and then put this vector on a diagonal matrix, and this is your partial trace. So your partial trace is a diagonal matrix. Yeah. And the same for the other partial trace. You multiply A with the all one vector, but from the left. Okay. So all these properties which appear a lot in quantum information theory are very, you can express them very nicely in terms of these parameters A, B, C. That's the point. And this is the conclusion. So I could very well stop here, and I think maybe I should stop here, or I can continue for a bit. It's up to you. But this is a good point to a good place to make this claim that these families indexed by matrices A, B, or ABC, if you look at the orthogonal case, they are a very nice set of families. So you should think whenever you need an example of a bipartite state with some simple properties that you can play with and you can do analytical or numerical computations. Think about these families. I recommend you to think about these families because they are parameterized by three matrices, so no tensor products, nothing, just usual matrices A, B, C, and their properties like positivity, partial traces, PPT, all these things, they can be easily written down in terms of matrices, so no tensor product, right? So I can express properties of this matrix X, which is bipartite, so it has this tensor product between Alice and Bob, in terms of just one partite matrix. So I have this drop in complexity. So this was also true, the same thing was also true for Vernon isotropic states, but what I claim is that actually these families are much bigger and they contain many interesting phenomena, and such as PPT entanglement, and I can tell you about PPT entanglement later. But this is basically my take-home message is this is a very nice family of states, of symmetric states, which you can do many computations with and play around with. It encompasses many known examples of interesting states, and it's very easy to work with. So it's a good point to ask if there are any questions to this point.
So I have some simple questions.
Please go ahead.
So these parameterization of these states, how is it related to like extreme points of the set? Because these are convex sets as well, right?
Yes, very good. It's a very good question. So in this paper we have with Sadvik, in the second paper that I recommended at the beginning of the talk, we characterize extremally of these sets. So it's you know, so you can think of there is this condition that A and B have to have the same diagonal, but if you forget about this, then really extremal points will be extremal points, either extremal points of this cone or extremal points of this cone, which we very well understand. I mean, these are extremal points of this cone are just, you have a 1 in some position in the matrix and 0 elsewhere. And extremal points of this cone, we understand these are rank 1 projections. So again, even for extremal rays, we have very nice characterizations of the extremal rays of this symmetric.
Sorry, I didn't know before. So entry-wise non-negative matrices, they have like it seems like you are saying.
It's just, you know, matrices which have positive entries, so the extremal rays are just a 1 somewhere. It's like the orthons, right? In Rn, it doesn't make a difference if it's a matrix or not, because you're looking at it entry wise. So
right. Yeah, one anywhere. Like, and more than one. Oh no, more than one thing. Okay.
So this the A part is much simpler than the B part. It's like classical.
Right, and also I think. Sorry. Yeah, go ahead.
So this is what I said, that A is the diagonal of X, right? A is the diagonal of my density matrix. So it behaves like this classical part of my density matrix. So it's much simpler. And B is like a sub matrix. It's a bit, it has quantum features, let's say.
So in that paper, you write the relation between the, like this characterization and extremal points, or you just characterize extremal points?
We characterize extremal points, precisely.
And what is the relation with the PPT criteria for separability for these states? Because for Werner and others, it was necessary and sufficient. What happens here?
This was my next slide. So let's see. You still 1 hour and a half. Yeah, maybe I can just finish with these 2 slides. I mean, because I think this is also like one of the points I wanted to make is that this family is nice enough that it contains PPT entangled states, and it's related to the leaky states. So now let's focus on these states of the form XAA. So it turns out, this is a theorem that we prove in our paper, that such a matrix XAA is separable. So this is a bipartite matrix, it's separable. If and only if the matrix A, so this is the only parameter now because I've taken B equals A. So it has to be, you know, it has to be entry-wise non-negative and positive semi-definite. But we ask something more. It has to be what's called completely positive. So this is a bit unfortunate because completely positive, we have completely positive linear maps, which are quantum channels. But it's not, it has nothing to do with this. It's a term which has been used in matrix analysis and optimization theory for a long time. It's unfortunately standard by now, so you might as well use it. So it has nothing to do with quantum channels, so it's not the same completely positive. What it means is that I can write A. So A is a real matrix because it has to be entry-wise negative. So I can write A as R times R transpose. I can always do this because A is positive semi-definite. But I asked that the matrix R, the square root of A, has no negative entries. So if I didn't have this, if I just had R here, then this condition would be just A is positive semi-definite. But by asking this, that the matrix R has no negative entries, this also guarantees in particular that the matrix A has no negative entries. Okay. And if you have such a decomposition, then you can have your separable. This is how the separable decomposition of X look like in terms of this completely positive decomposition of A.
So just very briefly, what was the proof idea that because how did you prove that this if and only for separability?
So this is easy because if I have such an A, I can just build a separable decomposition. Now I start from a separable decomposition from X, so I can write X as a sum of AI tensor BI. Okay. This is my separable decomposition for X sum. But I know that my X is CLDUI, so it has the symmetry. So what I will do, I will compute this. I know that this is the same as U tensor U bar, X U tensor U bar, star du. So this is called this twirling operation. So since X is invariant by this, it's equal to its average with respect to this. And when I plug this quantity into the average, it will give me a decomposition of this form. So I'm using the fact that X is symmetric to do this twirling. And by doing the twirling, I find the decomposition of this very special form, which is equivalent to my decomposition. So the short answer is twirling. And basically, you have to use the symmetry. You have to use your assumption that your operator is CLDUI. So you're using the symmetry to get a very special form of separable decomposition. And
I'm still curious about the other class that if I have block diagonal structure, then it looks like that these results will go through about separability and the characterization and everything.
I mean, definitely we don't consider this in our paper, but yeah, we can think about it. Yes, I don't know, to be honest. We didn't think about this. We didn't think about this more when you have symmetry just on some legs and not on the others. I don't know.
Okay.
So we have a characterization for separability in this particular case when A equals B. And now, as I told you, these completely positive matrices, they have been studied a lot in optimization theory because you know the definition. Remember the definition. You can think of them as Gram matrices of non-negative vectors. So you know every positive semi-definite matrix is the Gram matrix of something, of its square root vectors, but completely positive matrices are Gram matrices of vectors which have non-negative entries. You know, these RCM. Okay. So people have studied this a lot because you know most of the data in nature it's positive, it's not negative. So these Gram matrices appear all over the place, and they are used a lot in, for instance, in image processing. There is a famous algorithm using this. So they have been studied a lot. There are books written about this. And then I told you these completely positive matrices are doubly non-negative. So remember, let me write it again here. A is CP. If A is R times R transpose, where R is a matrix, R plus. And here the important thing is the plus. So it has a square root which has positive entries. So what I told you before is that this XAA is PPT if and only if A is doubly non-negative, and the same matrix is separable if it's CP. And it turns out that up to dimension 4, these two things are the same, being completely. So if you are positive semi-definite and non-negative entries, then you are completely positive. But it starts being false starting from d equals 5. So already from d equals 5, I can find a matrix such as this one. This is the example you find in all books of a matrix which is doubly non-negative. It has no negative entries. It has positive eigenvalues, but you cannot write it like this. You cannot find a square root which has no negative entries. And this matrix, if you put it back through our machinery, through our identification of these CLDUI states, what you will find is precisely a PPT entangled state. So we are able to use this machinery, I mean, these things which were known in optimization theory about doubly non-negative and completely positive matrices to come up with PPT entangled states. To be perfectly honest, this was not us. It has already been done before by Jordi Tura and some other people in a smaller class of this mixture of Dickey states, but we put it kind of in a more general framework. But the ideas were already there in this older papers. So yeah. So again, this is an argument why these states are interesting, because they contain PPT entangled states. And there is this very nice parallel with this theory of completely positive matrices.
But this is bipartite state in like dimension 25 plus 25, right? This is state.
This is exactly, this is X here. X belongs to M5, tensor M5. So it's a 25 by 25 matrix, but it's the Hilbert space of Alice and Bob have dimension 5.
Okay, so will it detect like the PPT entangle state below this size? I mean, the theorem says it doesn't, right? So how is it related to this 2 cross 3 and 3 cross 3 thing of?
Because 5 times 5 is larger than 2 times 3 and 3 times 3. So
Yeah,
PPT works when the dimension of Alice is dimension of Alice and Bob are either 2, 2 or 2, 3. And
yeah,
here
so
we are.
Yeah, so I was thinking that can this dimension be improved, or this is like some no kind of result that D has to be greater than equal to 5 to detect such states?
We can improve it, but not with this AA. We can improve it with different with more general constructions. But this is the cleanest and the easiest way to talk about PPT entangled in this, because it's also related to this very important notion of complete positivities. This is the nicest way to introduce them, but we can do much better than 5 times. I mean, we can do 3 times 3. Which is the smallest case not covered by this PPT. Yes, so this is one example for which these states are interesting. And then I will finish by this. I will not talk about this, but maybe just so these are some technicalities. So since they were so nice with respect to PPT and separability, we tried to see whether we can find counterexamples to this PPT squared conjecture in this family of states. And the answer is no, actually. So the PPT squared conjecture holds for our class of matrices. So in order to find counterexamples, you need to go outside of the classes. But definitely, I don't want to talk about this because I will have to go a bit into the PPT squared conjecture. And this is kind of a, if you are looking for counterexamples, this is a negative result. If you think the conjecture is true, it's a positive result. It's a matter of taste. Again, some technicalities, and let me end with this slide to summarize a bit what I've been telling you about. So the main idea is that we want to look at states which are symmetric with respect to diagonal unitary operators. And the keyword here is diagonal. So instead of looking at the full unitary on the Alice and Bob Hilbert space, we're just looking at phases on the diagonal or signs on the diagonal. Moreover, this is what Abbas, we have this recent paper with Abbas and Sadvik about. We have this diagonal unitary group, but now we can add some. So we have that the symmetric states are interesting. What if we add a little bit more symmetry to have even fewer parameters? The answer is we can add, for instance, cyclic permutations inside my D by D unitary group, and then we still get PPT entangled state, and we call this cyclic permutation states. So you can add a little bit more symmetry, not too much. If you add the full permutation symmetry, then you get these hyperoctahedral states, which are too simple to contain PPT entangled states. So we think that this is, again, you can make the class of invariant states even smaller and still get PPT entanglement. This is the point that you have this family of states of size d squared times d squared. So you have d to the power 4 parameters in total, but you have the subclass now of symmetric states which only has of order d squared parameters. And this family is still rich enough to contain PPT entangled states. And there was this final result that it satisfies the PPT squared conjecture. So if you want counterexamples, you have to go outside of this family of states, but that's a different story. So I think it's a good time for me to stop. Thanks so much for listening. And thanks for all nice questions.
Thank you. If there are any questions, please ask. Anyone has any questions?
If no one, then I would like to ask some more.
Sure, Uttam.
So if I want to know about say generic entanglement in these states, Do you think that there will be some concentration kind of result on this subset of states? Like if I pick a random state from this set.
Yes, so this is again a paper that I mentioned at the very beginning. So we have this paper here. It's called the random covariant quantum channels, but as you know, if you think of quantum channels in terms of Choi matrices, what we could have called this paper is random bipartite quantum states, the same thing. And here we look at some natural probability distributions on the set of channels or bipartite states having this type of symmetry.
Mm-hmm.
And we study what are the generic properties of these states. So if you're interested in generic properties, then have a look at this paper from last year.
I see. Thank you.
If there are no other questions, let's thank Professor Nechita for once again for giving the talk.
Thanks so much.
Thank you. So we can call off the talk right now. Nice to hear from you.
Thank you. Thanks for your patience and for the very nice questions.